Hello, everybody. Thanks for joining us today. For those who don't know who I am, because it's usually Ruth in this situation that does the welcome, but my name's Jodie Salenga and I'm the Business Development Manager here at BFBI. On behalf of Nijhuis, welcome to our breakfast briefing on how to reduce carbon and recover renewable biogas and energy. You've been automatically muted to keep feedback to a minimum, and we ask that you switch your video off to keep the bandwidth to a maximum. Please do post your questions in the chat, and we will ensure that all the questions are fed through to our presenter, Andy Burgess, at the end of the presentation. Any specific organisational questions you'd like to raise with Andy, we can put you in contact with him after the webinar. At the end of the session, we'll be sending on a feedback form, which helps us understand how we can improve and gives you the opportunity to suggest future subjects of interest. We really would appreciate if you take the time to complete this. It really does help us. The briefing is being recorded and we'll post it on our YouTube channel, which will then circulate down to our social media platforms in the coming days. And the slide deck will also be available for you as well, which will be sent out with the feedback form. So thank you for supporting and logging in this morning. I hope it provides all the information to support you and your needs. And I'm going to hand over to Andy, our presenter. Thank you.
Thanks for the great introduction. Appreciate it. So, Andy Burgess, who am I? I enjoy climbing. Very proud of my 2-year-old, and from a work sense, my passion is generating value from wastewater. And ever since completing a chemistry degree at Sheffield University, I've progressed through various laboratory consultancy roles in terms of wastewater treatment, and now progressing to the leader in Nijhuis when it comes to the design, build, operation and maintenance of large-scale and modular systems when it comes to wastewater treatment, physical, chemical and biological. And thank you all for joining today and giving me some time before starting work. So yeah, I hope you find this interesting. Yeah, let's get started. So what are we here to talk about today? In the market that we're currently in regard to the food, beverage, milk and industrial sectors, there's a big push, not only from a cost point of view, but also from a sustainability view in terms of how can we reduce carbon and recover energy on site. This presentation is going to be focusing on how we can recover energy from your wastewater. So what we're going to talk about today, we're going to talk about a specific technology, anaerobic digestion specifically, and what are the benefits of this technology when it comes to recovering energy from your wastewater and reducing your carbon usage on site. We're going to give an example of the technology so you can understand what this looks like and what are the key process steps required. We're also then going to go into a couple of examples which highlights the value in terms of typical scenarios which can provide a sufficient payback to justify the technology. We're also going to provide some information on our historical references as Nijhuis when it comes to anaerobic digestion. And then finally, the key steps that we need to go through when we're understanding how do we know if our site is suitable for anaerobic digestion when it comes to our wastewater. So first off, what is anaerobic digestion? So on site at the moment, you will have likely have a wastewater. And if we're using brewing as a typical example, we have bacteria that convert sugars to alcohol. When it comes to anaerobic digestion, we have specific bacteria that convert the inorganic and organic pollutants in your wastewater, deemed the sort of technical term here, and also on your discharge consent list, is COD, or chemical oxygen demand. And this is the sum quantity of the inorganic and organic pollutants within your wastewater. And we have specific bacteria that convert this COD to methane. And why is methane a benefit in terms of a product? That's because it can be used as a sustainable fuel for either feeding a boiler or CHP, heat or electricity. Another benefit from anaerobic digestion in terms of the bacteria itself is that because it is in a granular form, and you'll see a picture here, which looks a little bit like caviar, probably doesn't taste the same, but visually it's quite similar. And that biomass is also actually a value. There is a market available for the sale and purchase of this biomass to start new anaerobic digestion processes, wherever that site may be. And on the right here, we have an example of what an anaerobic digestion reactor looks like. So it's kind of typically a pre-acidification stage, followed by the anaerobic reactor itself. And in the bottom left-hand corner of that picture, you'll see sort of an infographic which shows some suspended granules and then a upflow of effluent from the bottom to the top of the reactor, which is then recirculated. The biomass is then held in that suspension, and the biogas is collected from the top. The key thing here is that the conditions for the bacteria, it needs to be around a neutral pH and between 25 to 37 degrees to keep the bugs happy. So yeah, key things to note from this slide is that anaerobic digestion, we're converting the organic pollutants in your wastewater to methane that then can be used to either heat water in place of natural gas, or to feed a CHP to produce sustainable electricity and recover heat. So we've talked a little bit about what anaerobic digestion is, and how can it be employed on your site? But what are the benefits? What is the key benefits that can be recovered from implementing this technology on your site? One is from a regulatory perspective. Whether you're discharging to river or sewer, you need to achieve a certain amount of reduction of the pollutants. High rate anaerobic digestion is a fantastic way in which you can reduce your COD concentration within your wastewater by up to 95%, without the need for aeration and costly biomass disposal in comparison with aerobic treatment. It can also be used as a tool to support your net zero targets, where ultimately, if we are, instead of discharging that COD to watercourse or using air for conventional aerobic treatment technologies, which has a carbon cost, because we're recovering that COD into methane, we're actually recovering that CO2 and using it as a sustainable fuel source. And just for an indication, about 6.5 tons of CO2 per ton of COD could be recovered. That's kind of the COD, the CO2 equivalents. And then we get on to the sort of OPEX cost saving side of things. As I mentioned, the biogas can be used to feed on-site boilers to offset natural gas. Can also be used to feed a CHP in terms of a sustainable fuel source to produce sustainable electricity, another energy cost saving. And if you are discharging to sewer currently, it can be employed to reduce your sewage discharge costs by reducing the amount of COD in your wastewater. Another great benefit of the anaerobic digestion process compared to conventional aerobic treatment processes is that it is a very small footprint. You're not looking, and we've got an example further on in the presentation, but we don't have sort of, large aerobic tanks of hundreds and hundreds of meter cubed capacity. It is a very compact technology, and the OPEX costs associated with it are mainly focused around the heating of the wastewater, if required. But there's no costs for sludge disposal. The biomass is actually a value that can be sold, and there's no aeration as it's an anaerobic treatment process. There's no aeration required compared to conventional treatment. But the key considerations that you need to be thinking about in terms of, is my site suitable, is that you need to ensure that you've got the appropriate strength of wastewater. And when I say strength of wastewater, I mean the COD concentration. So typically your COD concentration needs to be above 2,000 milligrams per litre COD to be suitable, because the bacteria have to have the right food to mass ratio for efficient conversion and production of methane. So now I'd like to give you an example to see what the technology actually looks like, and go through an example of one of our standardized modular systems. Although we do bespoke larger assets, but this can give you a good example of what an anaerobic digestion process looks like. So this is an example of our standardized eco-reactor. And what you can see here is a containerized control module and flare stack. The flare is in place to, if the biogas cannot be utilized on site for a reason, it's basically a safety precaution that the biogas is burnt via a flare. And what we have next to that control module is the reactor itself, that is held at around 25 to 37 degrees, depending on the specific design, and holds the biomass in suspension, and has the biogas collection within that as well. So yeah, hopefully that gives you a bit of an example of what the technology looks like. And this is sort of a prefabricated standard technology for our modular solution. In terms of what is the operational time associated with this, it's typically 1 to 2 hours per day in terms of a visual planned preventative maintenance check. And this reactor size is typical for about treating 3.2 to 5 tons of COD per day. So that kind of gives you an example of the loading rates achievable, but we do have more information on this on the following slide. So you can start to think about, well, how much COD do I need to have in terms of a total load? And when I say total load, I mean the sum in terms of mass of the COD over a 24-hour period. So this gives an example of the two standardized modular systems that we have, which provides a maximum hydraulic flow rate as well as some indicative loadings. So what you can see here is that the min to maximum COD loadings for these modular reactors is between 300 to 5 tons per day of COD. And the greater the load per day, the greater return on investment if you're looking at this from a financial perspective. But if you're purely looking at it from a compliance perspective versus aerobic treatment and reducing those operational costs and saving that carbon, then that can give you an idea of, what is the minimum loading that could be suitable. And it also mentions some figures there based on the amount of biogas produced as well. So next, I'd like to go through a couple of examples, a couple of case studies. So we've highlighted what anaerobic digestion is, what the reactor looks like, and gone into a few details of the specifics around the design. But ultimately, when it comes down to implementing this on your site, from a recovering carbon, but also recovering value from your wastewater, it's good to understand, what are the potential benefits when it comes to appeasing the finance manager. So I've done a couple of scenarios. First one is based on if we are utilizing the biogas for an on-site to offset natural gas, as well as saving on sewage discharge savings. So this is a site where we've got a on-site boiler that can potentially take methane instead of, in a combination with natural gas, normally designed with a dual purpose burner. And we have a site that's currently paying to discharge their COD to sewer. For this particular site, the flows were around 600 meter cube per day, and the COD concentration was 5,000 milligrams per litre. So you can kind of use this to compare against your site to, think about where you might end up from a sort of business case perspective and flow and load scenario. But the key takeaways, rather than reading out all of these numbers, is that typically from a sewage discharge perspective, if you don't have any treatment currently in place, then you've got the potential to reduce your sewage discharge costs by about 50%. And in this case, we've got potential to, have sort of £125,000 worth of savings in comparison to offsetting your natural gas. So it's essentially replacing some of your natural gas usage with biogas. And for this application, it was a sort of £1 million saving per annum. So, if you've got the right flow and the right load, it can be very attractive. So that's one example based on utilizing the biogas produced from your effluent to offset natural gas and save on your sewage discharge costs. And then we have another scenario here, and this is based on a slightly lower flow rate and a different site scenario. So for this scenario, the customer was not discharging to sewer. They were discharging to watercourse with some existing aerobic treatment. So what I'm trying to demonstrate here is, what are the benefits of anaerobic digestion versus aerobic treatment? And so, sorry, I lost track slightly there. So so what are we talking about? We're talking about the application. Oh, and also the application for this one is utilizing the biogas produced from your effluent to feed a combined heat and power system to generate electricity and heat. And the key thing when it comes to implementing a CHP on site is that you're not just producing electricity, you're also recovering the heat, which can be utilized on site. So the savings for this example that we've got are allocated to recovering energy, reducing aeration costs and carbon by 90%. And because anaerobic digestion, the biomass produced from that system, is actually of value compared to aerobic sludge, which needs to be disposed of and treated at a high OPEX cost, we've got a number of key savings. So what we can see here is that the highlighted boxes on the left-hand side, we've got the waste heat value, we've got the energy savings, we've got the savings on the aeration compared to aerobic, and also the savings in terms of sludge disposal compared to aerobic system. So for this application, we've got savings of around £340,000, and that's for a COD concentration of 6,500 milligrams per litre and a flow rate of 112 metre cube per day. So in terms of, this would be a long-term payback, but in terms of, a compliance driver versus aerobic treatment, you can definitely see here that anaerobic digestion provides a value rather than a cost. And, a value summary when it comes to a carbon perspective of around 129 tonnes of CO2 recovered per annum associated with aeration savings and biogas recovered. So I guess what I'm trying to show there is a couple of examples based on no existing effluent treatment plant and discharging to sewer, and an example where we're discharging to watercourse, utilising CHP and in replacement or instead of aerobic treatment technology. I won't go through these in too much detail, but just a point to say that, anaerobic digestion, it is an established technology. In Nijhuis, we have over 112 references utilising our standard systems all the way through to bespoke large-scale assets up to 19 tonnes of COD per day. And I think the most recent asset that will be that is currently in commissioning in the UK is 60 tonnes of COD per day. So yeah, an absolute monster. But yeah, I suppose the thing is, anaerobic digestion, it's an established technology. So in terms of risk associated with implementation are really relatively low. And yeah, I'd be happy to take anyone to one of our sites to have a look in a bit more detail if they're interested. One example here just highlights one of our eco-reactor installations where we are, where the actual load for the reactor is all the way down to 0.5 tonnes of COD per day, just highlighting that if you are a small manufacturer and you have a small load, it still can be successfully implemented. And then finally, well, almost finally, I've got one more slide after this, is just to go through, if you'd like to reach out to understand more and see whether anaerobic digestion could be feasible for your site, what would be the potential carbon saving if that's the driver? What would be the potential OPEX cost saving and payback if that's the driver for you? Then, please don't hesitate to reach out with the contact details on this slide. And if you'd like to do some preparatory work before that, by all means, if you could put together some data based on your average COD concentration, your flow, your effluent flow, what your pH levels are, effluent temperature, what's the total suspended solids for your wastewater, and then maybe some cost information on natural gas usage, sewage discharge costs, aerobic treatment costs, spelled correctly probably from yourselves, I'm sure, not like I've messed it up there. Then that would help us to be able to do a quick feasibility assessment and come back to you with a high level design and understanding. And then just a quick comment on Nijhuis. We are a complete solution provider for water and wastewater treatment, because although it might have sounded like I was bad-mouthing aerobic treatment, it's not that it's not the right solution. It's just that, given the right flow and load, anaerobic digestion can be a fantastic opportunity, because Nijhuis has a complete technology portfolio that covers all manner of physical, chemical, and biological treatment, all types of aerobic treatment, anaerobic treatment. So although I've been kind of tailored towards a specific technology, we are not biased towards that. And we're unrivaled in the UK to support from a upfront feasibility. We have in-house flow and load capabilities all the way through to ongoing operation and maintenance and EPC design and build. So yeah, I think that's all that I wanted to go through today. So yeah, welcome any questions at this point.
Anyone have any questions for Andy? I know I've got a couple. Well, I'll start off then, Andy. You touched on earlier in your presentation about the sort of footprint of the wastewater sort of technology. But is it something that would be sort of suitable for that sort of urban/city environment, or is it something where you do need a little bit of space, even if it's smaller in comparison to other technology?
Yeah, so footprint is important. If you're in a heavily built up area if you don't even have space for a 40-foot container, then it's not going to be suitable.
Yeah.
But if you what I'm just showing on screen now, that's an example of the control system, flare and reactor for a small system. There would need to be a balance tank to balance your effluent as well, if not already in place. So footprint is definitely a key consideration. So when considering the technology, it's definitely a really important thing to take into account.
And that's suppose that leads on to my next question is, is there a sort of a minimum size of beverage facility that can sort of sustain this capital investment?
Yeah, no, that's a really good question. And it really is all down to the key elements that I mentioned in when I start to talk about the feasibility assessment is
Yeah.
ideally to make a quick assessment, you need to be able to quantify the total COD load per day and the concentration. Once you have that information, then it's easy for me to do a quick assessment. But as I say, the sort of minimum COD load you need to consider the technology is, say, 500 kilos of COD per day in your wastewater, and a minimum concentration of 2,000 milligrams per litre COD. But the stronger, the higher the concentration of COD, the better. And as I say, the COD load as a total mass per day needs to be above 500 kilos per day.
Okay, perfect. Thank you. Is there
Thanks,
any
that
other?
Jodie.
No problem. I know you, like you say, you touched on both of those points, but I just wanted to sort of have you reiterate sort of the footprint and sort of the minimum size of facility. But it looks like that you will, like you say, assess any facility to see what could be tailored for them. That's correct.
Yeah, no, that's it. Thanks, Jodie.
Perfect. Is there any other questions for Andy? Feel free to unmute yourself if you have any. Oh, can I get a link to the recording? I was late joining. Yeah, of course you can, Jim. So this has been recorded from the beginning, and we will be posting it on our YouTube channel. So I just have to do some editing, and then that will go out for everyone to view. But thank you everybody for joining. If there is any more questions, I will give you Andy's contact information in my follow-up email so you can talk to him directly.
Awesome. Thanks,
Thank you.
everyone. Thanks, everyone, for joining. Cheers.
Thanks, Andy. Thank you, everybody.